In section 5.2, we're going to be looking at some properties of rational functions. So we should start out by saying what a rational function is. If we have two polynomial functions, p of x and q of x, then a rational function would be r of x equals p of x over q of x. So a rational function is just a fraction that is made up out of two polynomial functions. But we have to be careful because we've now introduced a domain restriction because our denominator q of x cannot equal 0. So that brings us directly to domain. The domain for a rational function is going to be all real numbers except the ones that make the denominator equal 0. To write our rational function in lowest terms, we will need to make sure there are no common factors. So what does that tell us that we have to do, like action-wise? You're going to factor and cancel any common factors. We'll get plenty of practice with that because canceled factors are going to look different than non-canceled factors. We'll get to that here soon. There are two specific common rational functions that we can graph using transformations. The first one we've seen before. It's y equals 1 over x. We call that the reciprocal function, and it's kind of the parent function for the rational family. The reciprocal function is the one that had the, I need a different color. It's fine. It's the one that has the force fields coming out of that black hole at 0, 0. So it had the black hole at 0, 0, and then it has a vertical asymptote coming out of the black hole and a horizontal asymptote also. The ordered pairs that we use to graph this, if we input a 1, then we'll output 1 over 1, which is also 1. If we input a 2, the output will be 1 over 2, so 1/2. And if we input 1/2, we'll output 1 over 1/2, which would be 2. So those are our ordered pairs: 1/2, 2, 1, 1, and 2, 1/2. I mentioned before that we have this horizontal asymptote. I'll just abbreviate that by HA. That's horizontal asymptote. And that's at y equals 0. And then we have a vertical asymptote at x equals 0. So our graph is not going to cross either one of those, but it is going to run along both asymptotes. So it'll run along there, kind of down in the corner, and then along the horizontal asymptote. Now this graph does have origin symmetry, which means if I rotate 180 degrees, I should have the exact same thing. So my matching ordered pairs over here will be -1, -1, -2, -1/2, and -1/2, -2. And then we're going to have that symmetrical piece down in the third quadrant. The domain for this function is going to be all real numbers except for 0. So we go -infinity up to 0, skip over 0, and start again to infinity. So -infinity to 0, union with 0 to infinity. And the range is going to be the same way. If we go bottom to top, -infinity up to 0, skip over it, start back up again. Now I did mention that we can use transformations on these functions. So the black hole is not always at 0, 0, but it always does play a part in our domain and range. So when you're figuring out your domain and range, you want to remember that you're going to skip over the vertical asymptote in the domain and skip over the horizontal asymptote in the range. The way that we apply transformations to this function, so we'll have y equals 1 over x is our general function. And then we might have a number multiplied out front. Sometimes you'll also see that number up in the numerator, but it's going to mean the same thing. So that will be a vertical stretch or compression. It's a stretch if that number is bigger than 1. It's a compression if that number is between 0 and 1. Remember, if that number is negative, that is going to be reflection over the x-axis. This graph can shift left and right by adding or subtracting a number in with the x, so down in that denominator. That is going to shift left if it's added and right if it is subtracted, just like it did in all of our other function families. And then we can shift up and down by adding or subtracting a number that's separate from the fraction. So this will shift up if it's added and down if it's subtracted. The other parent function that we're going to look at is y equals 1 over x squared. So now when it's going to have that same black hole. So it'll have a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. I still can't divide by 0, so 0, 0 is the no zone. Then if I input a 1, 1 over 1 squared is 1. If I input a 2, I'll have 1 over 2 squared, which is 1/4. So 2, 1/4, 1, 1. And if I input a 1/2, then I'll do 1 over 1/2 squared, which is 1 over 1/4, which would be 4. So 1/2, 4. Still following along the asymptote through those 3 ordered pairs and then along the other asymptote. Now this one is slightly different because it is an even function, whereas y equals 1 over x was an odd function. So instead of having origin symmetry, which odd functions do, this one is an even function, so it's going to have y-axis symmetry. So these mirrored pairs are going to be in quadrant 2 instead of quadrant 3. So y equals 1 over x squared looks like that. And it can have the same types of transformations that y equals 1 over x could have. We could have a number multiplied out front. We can have a number added or subtracted in with the x squared. Or we can have a number added or subtracted at the end. And those will all mean the same thing. What about domain and range? Domain for y equals 1 over x squared, left to right, we have to skip over 0. So domain, negative infinity to 0, and then 0 to infinity. Range, if I go from negative infinity up, the first y values we start having are 0, but we can't include it because of the asymptote. So we will go 0 to infinity with a parenthesis on both. Okay. I think I'm going to pause here because these functions are the ones that I just showed you, parent functions. They always just have like a 1 in the numerator or a number if there's a stretch or compression. And then the next ones we're going to look at have variables in the numerator and denominator, which is like kind of a different category. So I'm going to do that one in a different video.